Okay. All right. So, based on some statistical understanding that we had from the preceding discussion, um, let's now go back to the regression analysis. Okay. And what I'll try to do is to, as we go along, we establish the connection between regression and linear models. Okay. So we maintain that if we talk about regression only, right? I mean, if we talk about regression only, it's a statistical method, right? So primarily the analysis is statistical, right? Uh, but however, if we keep it that way, right? I mean, if we keep it that way on toy examples, it is sort of manageable. But the moment we have a very large pool of data, right? So if we want to do it on a large number of observations, and if we have a large number of observations, right? And we intend to do it purely based on a statistical way of thinking, then this incurs a lot of bookkeeping. Okay. Now, in order to mitigate that, we try to do some abstraction of the statistical analysis. So an abstraction of the statistical analysis okay, to mitigate the bookkeeping, right, is done through linear models. Okay, and therefore, so this abstraction is due to linear algebra. Okay, the methods that we have mostly studied in this class. Okay, so this is broadly the idea, right? However, I mean, before we get there, there are a few things about uh, basic statistical analysis or basic regression analysis that we need to understand, right, before we can make such a jump, right? Okay. And so it's basically, it's nothing but, uh, I'll come to the point of why I'm calling it linear regression, right? I mean, but what we really want to do is that there is some data, right? And there is some independent variable, let's say just one independent variable, and there is one dependent variable, right? And what we just want to study is the relationship between the two, right? Okay. So, so there is this, you know, dependent variable, right? And an independent variable. Let's say just one for now. Okay. And the idea is that we try to figure out a function. Okay. Try to figure out a function. Now, how do we figure this out? Right? So the question is, does the model drive the data or the data drives the model? Okay. So here, the assumption is that we know that there are tons and tons of models that exist in nature, right? And one of such models will describe the data under consideration. That's the assumption. Okay. All right. So let's say the outcome of a process, any process is denoted by a random variable. Okay. So let's just define this a random variable. Let's call it yi, right? And this yi is sort of for the ith observation, right? and this is what we call as the dependent variable. This is my dependent variable, right? And this depends on, so let's say this is yi, right? So this depends on a bunch of, let's say, independent variables. So now let's just think of a situation where we have more than one independent variable, right? So let's say I have k independent variables, right? And let's say I have k independent variables, x1 through k. Okay. And what I want to do is I just want to express the behavior between y and x by a function, right? And this relationship I would want to describe in the following manner. I can just use a vector, or for now, let's do it the bookkeeping manner, x1 through xk, right? Okay. And then if it's a linear model, it means a straight line. So each one of these will be accompanied by some coefficients. So let me write those coefficients here as well, right? Okay. All right. And plus some term. Okay. All right. Now this f is sort of, let's assume that we know this f. Okay. All right. And or we can assume this f, or we can guess, or whatever. And these beta 1 to beta k are the parameters which will characterize the role and the contribution of the independent variables x1 through xk towards y. Now, what is this epsilon? Right? This epsilon reflects the non-deterministic nature of the relationship. Okay? So this epsilon reflects, this just indicates a non-deterministic relation between y and x1 through x. Now, for example, if epsilon becomes 0, then what do we have? We have an exact relationship between y and these several independent variables, right? Okay. But if you really look at the real data, you would realize that such a non-deterministic relationship is usually not found in nature, right? Okay. So, but just for notation's sake, if epsilon is 0, this becomes a mathematical model. If epsilon is non-zero, this becomes a statistical model. Okay. All right. Now, the question about this, I mean, why am I calling it linear, right? I mean, why is the model linear? So what is the distinction between a linear and a non-linear model? So whenever I say linear or non-linear, what I mean or imply is that it is linear in parameters. Not in variables. Okay. All right. So, I mean, how do I check? How do you check whether a model is linear or non-linear? The way to check is to use partial derivatives of the dependent variable with respect to this parameters. Now, please understand that these parameters are unknown to us. Okay, and we should be able to figure out these parameters or estimate these parameters from the data, right? So therefore, I mean, what I'm looking at in order to check whether a model is linear in parameters or not, I need to be checking the del yi by, or del y by del beta j. Okay, so if this is independent of betas, right? If this is independent of beta, we will call this a linear model. Otherwise, it's an independent model. I mean, non-linear model. Okay, all right. So therefore, you can clearly see that the linearity or non-linearity of the model does not depend on the linearity and non-linearity of the independent variables x1 through xk. By the way, these guys are also called explanatory variables. Explanatory or predictor variables. Okay, and y is called the response variable or study variable. You can call it whatever you want, response or study variable. Okay. So if I give you an example, let me give you an example, right? I mean, so let's say I have something like this. So let's say begin with y equal to beta 1 square plus beta 2 square root of x2 plus beta 3 log of x3 plus. Okay. Now, this is actually, well, I don't need a y here. I mean, this is actually linear. Why? Because if you take del y by del beta 1, then what are you going to get? You're going to get 1, right? If I take del y by del beta 2, you're going to get 1 and so on and so forth. Okay, so therefore your partial derivatives, which means the rate of change of your response variable with respect to these unknown parameters, is not a variable, it's sort of a constant. It's a constant, right? So this is a linear model. So this is a linear model. However, if I take another example where the model is the following, just let's say y equal to beta 1 square x1 plus beta 2 x2 plus epsilon. Then what you can see here is that del y by del beta 1 is no longer a constant, right? It's 2 beta 1. So therefore, such models are non-linear. Okay, so our attention will only be centered around linear models. Okay, because we want to tie this up with the concepts that we have learned in linear algebra, right? Okay. So therefore, if a function is the function that you are about to determine is a function which is a linear function in the parameters, then it's a linear model. Otherwise, it's called a non-linear model. Okay, all right. So therefore, I mean, a general form of a linear model is like this. So therefore, a general form of a linear model is like this. And y equal to beta 1 x1 plus beta 2 x2 blah 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 beta k xk plus. Okay, so this is what a linear model is represented. This is how a linear model is represented. Okay, so this k depends on the number of data points that we have, right? The idea of regression is just going backwards. In the sense, I mean, the meaning of the word regressing means it means that we go back. Now, what do we mean by going back or going backwards? Is that I say that this is the model that I have, right? And I have the data points, and I plug in those data points in the corresponding y values, because for a certain set of data points, these y, x1, x2, xk tuples are already known to us. What is the idea? The idea is, if new data comes in, right? If I have new data, then how good this existing model is in terms of fitting it to the new data. So what are you trying to do? You are trying to infer a larger space of data points, a larger collection of data points from a finite collection of data points, right? So if you really think about it, whatever values you have here, this y, x1, x2, all the way up to xk, this is nothing but a solution subspace of the entire space of data points that you could possibly imagine. Okay, all right. So using a subspace, you are trying to get an idea of the entire vector space. So this is how you should make the connection. So how do you do it generally? If I may ask you this question at this point of time, I have a subspace and I have a superspace of a subspace, right? How do we infer things, or how do we generalize things from subspace to superspace, or the other way around? So what tools in linear algebra we should use? Any idea? You are familiar with the tool, so I'm not asking anything new or asking you to think beyond the scope of the subject. Anything? Any idea, guys? No? You want a hint? How about some projection? Make sense? How about some projections? No? Nobody? Vipin? Milan? Any idea? Tanish? No? Ria? Okay. So just think about this. Well, how do I match? I mean, matching as in, how do you match? So in general, I mean, when we talked about projections, I mean, what was the general idea of a projection? That, I mean, I have some solution in the operator space, right? In a large space, right? When I project it in the direction of something, what am I essentially planning to achieve? Some similarity, right? Okay, which I usually do by computing the inner product. Correct? Okay. So if I have solution space, I mean, if I have a large solution space and the data can come from anywhere, right? But when you are training a model, I mean, you train with limited data, right? So the idea is when you are going backwards in regression, the idea is that using the trained model based on whatever available data you have, you try to infer a model which fits a larger pool of data points, a larger pool of observation. So in other words, if you flip it, if you really flip it, what you are achieving is that you are trying to project the large solution space, data points from the large solution space to its subspace, isn't it? And how do you do the projection? Usually the most efficient of projections are orthogonal projections, right? The most efficient projections are orthogonal projections. So you take a vector in the solution space and you orthogonally project it in the direction of another vector, and this particular vector is your fitted line. Okay, this particular vector is nothing but your fitted line from the available data points, right? And when you do this kind of an orthogonal projection, what you get is try to get some similarity of a larger set of data points from the set of data points that you already have, which is exactly what your model is trying to achieve, right? Because what you are claiming is that my model is good for this particular set of data points, which is the data points from x1 to xk, right? And now I have a larger set of data points x1 to xk, xk plus 1, blah, 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 all the way up to xn, where n is much, much larger than k. So what I'm trying to do, I'm trying to project a vector from the solution space which might contain x1 through xn to a solution space which only contains x1 through xk. And I achieve it by dropping a perpendicular from that vector onto this vector. Okay, and the whole purpose of orthogonal projection is to project that larger set of solution points onto a smaller set of solution points, right? Assuming that there is some similarity between the two. And this similarity is drawn by how good your fitted model is. So if your fitted model is pretty good to a larger set of data points that you have not seen, right? Then that means your fitted model is similar to another model that you are going to validate with those larger set of data points. And those two models are pretty close to each other, right? So remember, the larger data points which sort of gives us a function that is a function of exact values, right? And the smaller set of data points is a function which is given by your linear regression model, is a function that gives us the predicted values, right? So, and the idea is how close are these predicted values to the actual values. And the way we determine this closeness or proximity is by computing the least square distances between the two. And how do you compute the least square distances? You compute the least square distances by dropping a perpendicular from one vector in the direction of another vector, right? Okay, and that's how this whole idea of projections, least square optimization, and regression come together. Okay, all right. I'm going to get back to this idea again later on, right? So now, so this whole idea. So therefore, if you develop a linear model, like a linear algebraic model, then naturally, if you use matrix notations and crisp matrix notations, you will be able to handle. You really do not have to, worry about the number of data points you are going to handle, right? And so therefore, it saves you from a lot of bookkeeping. That's the whole idea of talking linear models and linear regressions in the same breath. Okay, all right. So we are working on the assumption that the model generates the data, not the other way around. Okay, all right. So therefore, I mean, with this, I can now go and sort of formalize the regression model itself, right? Okay. So if I have to do that, my formal regression model is just, I mean, if I take an example that I have a formal regression model, which is beta 1 x1 plus beta 2 x2 plus epsilon. But this epsilon, I'll come to this epsilon later. And so let's say this is like crop yield. Just imagine this is crop yield, right? And there are two explanatory variables. One is the quality of the fertilizer, right? The quality of the fertilizers. So you can see a regression model is able to handle both qualitative and quantitative variables, right? And X2 is, let's say, the level of irrigation. Okay. All right. Then I'm assuming that there exists a linear model which is able to fit the data. Okay. All right. And so there exist some values of beta 1 and beta 2. There are some true values of beta 1 and beta 2 that we know exist, but we just don't know them yet, right? So what you do is that we record some values of y corresponding to some values of x1 and x2, right? Okay, figure out the relationship, and from that relationship estimate the values of beta 1 and beta 2, okay, by regressing it in the backward direction. Okay, so this approach is basically what is known as a regression analysis. And needless to say, when you say my model is good, there are some measures of goodness, right? I mean, measures of the central tendency, so on and so forth. And we discussed last time some of these measures of central tendency, like we can use a mean and we can also use a variance, right? Since these guys, these x1 and x2 are deterministic variables, and y is the only random variable here, right? Okay, so when I talk about central tendencies of y, I only mean that the mean of y and the variance of y. So these are some of the tests that we need to do in order to see how good my model is, how much is it varying from the average value of y, how much it is varying from the fitted, predicted exact value of y, so on and so forth. Okay, so there are many steps in regression analysis. One of the steps is a choice of a relevant variable. If you recall, we discussed this by giving an example between equilibrium temperature and surface temperature. And there we argued that how this is not a regression problem at all, right? So this is a regression problem because you can see the units of the variables are different, right? And also the observation, the sources of observation are also different, right? The quality of the fertilizer is a different explanatory variable than the yield of crop, and as well as the level of irrigation, right? The sources of observation are different, and therefore the units of observation or the units of the variable are also different. So this is a statistical problem. Another statistical problem could be, I mean, can you regress between length, height, and weight of individuals? In other words, if I know the weight of an individual, can I figure out, can I predict it is either her height or the other way around? Okay, so, and then there has to be some model specifications and model assumptions, right? Okay, so therefore, in general, when we criticize a model, we actually have to go back and look at where our model has failed us, or where we actually failed the model. Okay, and this is attributed to typically the kind of assumptions that we usually take. Okay, and there comes the role of epsilon. Okay, so we assume that epsilon is a normally distributed random variable. This assumption is not used at all while estimating the optimal values of beta 1, beta 2, and so on and so forth. But this assumption is used to verify if the values that we obtained for beta 1 and beta 2 are correct to a confidence level, or if the hypothesis that my data is represented by this model is correct to a level of confidence. Okay, that's the only point where this is used. Okay, now there are also this there are different types, I mean, of data that we have to deal with. If we have purely quantitative data, we don't really have to worry much. But if we have qualitative or categorical data, we need to figure out a way to convert it to a quantitative variable. Like, let's say if there are 3-4 qualities of fertilizer, we can express that in terms of quantitative variables as, you know, -2, -1, +1, +2, or so on and so forth, right? Okay. Similarly, the level of irrigation, if it is high, medium, low, we can assign quantitative variables to each one of these levels, and we can say 0, 1, or 2, so on. Okay. Basically, introduce a dummy variable. Okay. So there are some tests which are extensively conducted to measure the goodness of the model, and one such test is known as analysis of variance, or ANOVA, right? Okay. Analysis of variance. And this is conducted if your variables are explanatory variables are qualitative. So this is conducted if your x1 to xk are qualitative. Okay, and if the explanatory variables are both qualitative, some are qualitative and some are quantitative, then the analysis of the covariance technique is used. Okay. All right, so analysis of covariance technique is used if there is a mixture of qualitative and quantitative variables. Okay, so just to give you an idea in terms of notation and what kind of bookkeeping we have to do, I mean, it's just the sort of notation that are usually used in regression. So we have some, you know, experiment number, the number of times experiment or observation number, right? Okay, and there is this response variable. We know this is stochastic in nature, right? And then there are these explanatory or predictive variables. Okay. Now, what can be, so if we have, assuming that there are multiple explanatory variables, x1, x2, all the way up to xk, right? And now we have observations. Okay. So for observation 1, the value that I know or recorded is x1, is y1. And for explanatory variables, because for x1, this is the first value, so we use x11, right? Similarly, x12 and so on. So x1k. So for, and similarly, we repeat that notation as x21, x22, x2k. Okay, and this we go all the way up to, let's say if we go to number of observations as n, then the corresponding response variable value is yn, and then we have xn1, xn2, all the way up to xnk. Okay, and typically these n and k values do not match, right? Okay, all right. So having said this, the next question is, how do I do this parameter estimation? So there is a big question. The big question is parameter estimation, model parameter estimation. How do I do this? Okay, all right. So there are several methods. The most popular one is being least square optimization, or an ordinary least square method, right? And which is what we are going to discuss, right? Okay. Uh, so what really happens is, I mean, you do some parameter estimation, right? You get some values of beta, okay? And let's say you have beta k values, right? Okay. Now, as I have shown you in one of those examples from Raj Jain's book, is that it may or may not be the case that you require all of these parameters in your model. So it may sometimes so happen that you have by force introduced an extra variable, extra explanatory variable that was not really required to explain your model itself. And how do we know that? We know that by confidence intervals or CR. Okay. So when we do this parameter estimation, the first step of checking is that whether these values of these parameters is giving us a very good model fitting estimate. And how do I do that? I do that by measuring the distance between the actual value and the fitted value, right? And if this number is small, then I say that the parameters have fitted the model well. However, this does not tell us whether this model has additional parameters or not, because it may so happen that out of these beta 1 through beta k parameters, the fitted value that you have obtained has already reached a threshold, and after that you are simply overloading the model with additional or excess parameters. So how do I flush out those additional or excess parameters? I flush them out by computing the confidence interval for each one of these model parameters. And if the confidence intervals are good, which means the confidence intervals do not contain a zero, right? Then I will say that, okay, all of these parameters are good. If some of the confidence intervals contain a zero, I say that, well, these parameters are not required, so I can just flush them out. Okay, all right. So now when I compute this confidence interval, the role of epsilon becomes clear. Okay, because here you have to make some assumption, because your confidence interval tables are dependent on some z distribution, the z values and the t values, right? So they come from either the z values or the t values. Okay, so both are variants of the normal distribution. Okay, so that is why you require your epsilon to be normally distributed. So in other words, if I have to give a visual representation of what I mean the following. So let's say I have a model, something like this. Okay, and I have data points, something like this. Okay, roughly speaking. Okay, all right. So these distances that you see, right? These distances that you see are your errors, right? Okay. Now, what I want to see is that whether these errors are normally distributed or not. In other words, is there something like this? Is there some normal curve that I can trace about my fitted model? Are you getting the point? Okay. So if these are just, you have traced the errors, right? Okay. So if the trace is normal, okay, I can say that the epsilon is a normal random variable, and I can use this to determine the or estimate the confidence interval of the coefficients that I have computed or estimated. Okay, that is why this normal distribution on epsilon is important. Okay, I reiterate that this normality assumption is not used while computing the best fitted values of epsilon or to compute the least square estimates. Okay, Least square estimate is one technique, maximum likelihood estimation, and some other techniques are also there. But however, I'm not going to talk about those. I'm only going to talk about least square estimates because least square estimate has a direct relation with the linear algebra tools that we have already talked about. Okay. All right. I will stop today because I understand your exams are still going on. Okay. And we will reconvene on Friday. I hope things are clearer now. And also, if you have any concerns about the comprehensive proctored examination or final examination, please redirect your queries to the director or the head of the department. Okay, so I'm not the best person to answer these questions.
Uh, Excuse me, sir.
Yes,
Sir, I had sent you a mail regarding the assignment homework too. So, can you please look into it?
I have already looked into it and I have changed it. Okay,
Okay, okay, sir.
okay.
Thank you.